In this video we're going to look at permutations. The definition of permutation: a permutation of size R from a set of size n is an ordered subset of size R. So we're starting with a set of size n, and from that set we're picking R elements and putting them in order. And so in this case, order matters. So for permutations, order matters. Therefore, if we had, let's say we had an element A, B, and we also had the element B, A, those two would not be equal to each other. So order does matter for these permutations. So as a quick example, let's look at what are all the permutations of size 2 from the set here, A, B, C. So looking at our definition above, n is equal to 3 because we have 3 elements in our set that we're choosing from, and R would be 2 because we're choosing 2 elements at a time. So looking at the set, we could pick the first 2 elements, A and B, and put them in that order, but we could also pick those 2 elements in the opposite order, B and A. So we would have BA. And we could go through then all of the elements of that set, picking them 2 at a time, AC, CA, BC, and CB. So in this case, picking 2 from a set of size 3 where order matters, we come up with a total number of 6 elements possible for that permutation. Now, to be able to calculate the the number of elements that we would have in a permutation, we look at the notation that we would use. In this case, I'm going to use P for permutation. N is the number of elements that we're choosing from, and then R, the number of elements that we're choosing from that set of n. There are several different ways that you can represent it and see it in different books. Most of them use a P and then an N and an R. There's also this last method where we have N in parentheses with a subscript R. You can see any of those in different books. But let's look at how do we do this calculation for choosing R elements from a set of size n. So we have n elements in this set. Let's look at when we choose that first element from the set, how many different possibilities do we have? Well, we can choose any of the elements, and therefore we could choose n different possibilities for that first one. Once we've chosen that first one, we only have n minus 1 elements left to choose from. And so by looking at a product set, we would have n times n minus 1. Now if we were picking, let's say, 3 elements, then the next element that we would pick, we would only have n minus 2 to choose from. And this continues. I had to scratch something out here. This continues until you're with n minus R plus 1 as the last one that you're picking, the number of ways that you can pick that last one. Now another way we represent this is, notice that if we went all the way down and picked all of them, we would have n factorial, because the last one we would only have 1 element left, and so we would take this all the way down to 1, which would be n factorial. But if we stop sooner than that, with R being less than n, then we have to get rid of all those ones on the end. And the way we do that is by dividing by n minus R factorial. So by doing that, we would cancel with all the ones with the n factorial up above, from n minus R on. And so on the top we would just be left with this last one being n minus R plus 1. So this is how we'll represent that product. Sometimes I'll just write it out if there's only a few elements that we're choosing. Now notice that this is without replacement. So in other words, we pick one element out of that set and we keep it, and we don't put it back into the set and then choose again. If we allowed replacement, then we could potentially choose that same one that we chose the first time. And so if we did that, then the first time we pull one out, we would have n possibilities. And if we put it back into the set, we would have then n possibilities for the second one that we would choose. And therefore, with replacement, we would have n on the first, the first sample. Then if we put it back in the set, we would have n again. And we would have, therefore, n every time that we chose an element from that set. We would, if we were choosing r elements from that set, or we're choosing r times, then we would end up with n raised to the r. And so we would basically have n r times. Okay, so without replacement, we use this equation, and with replacement, we use this equation. So when you're doing your problems or doing your working something out, we have to first figure out, if we're doing a permutation or not, and then if we are we doing it with replacement or without replacement? There's another thing that could happen is that suppose we had a set that had some elements in it that were the same. We would call that a multiset. So the multiset is a set of objects, some of which are alike. So we might have two of the same element in our set. So in this case, suppose there are n elements in a set, and n sub 1 are alike. So we would have, maybe A or something like that in the set. N2 are also alike, and so on. So we might have several different groups that are alike. And in this case, we're saying we're going all the way out to n sub r elements that are alike. Now, if we're pulling out permutations or pulling out elements from that, and we're doing all of them, we're doing n elements, then of course we would have n factorial possible, but since some of them are alike, we don't have quite as many possibilities as an outcome because, we might choose the same element in different places. Because of that, we divide that n factorial by each of those numbers that are repeated factorial. So we n1 factorial, n2 factorial, and so on. Now let's do a real quick example here using that property. Suppose we have a set that has two elements that are repeated, A, and then we have a third element, B. So we've got three elements in this set. So the total, if we're picking three elements from this set, we know that we'll have 3 factorial different possibilities. However, because two of them are repeated, some of those choices that we pick will actually be the same thing. So if I give these like a A1 and A2, just so we can see where those come from, then we can see what happens. So I have A1, A2, B as one of the choices, A1, B, A2, and then A2, A1, B. Now you can see the other three that we have there, but let's look at these two here, A1, A2, and B, A2, A1, and B. Those two would be normally different elements. However, if we couldn't distinguish the two A's, A and A, then those are really the same element, AAB and AAB. If we continue through all this, we'll notice that we have these two will be the same, these two will be the same, and finally these two will be the same. If we take our n factorial and divide by 2 factorial, that leaves us with 3. And if you'll notice, we have 1, 2, 3 elements that are possible with that permutation, since we have A is repeated twice. Let's look at another example for just permutations. How many license plates are possible for a license plate that has 3 letters followed by 3 numbers, and we don't allow any repetitions? In this case, let's just look at the first 3 letters. Since we're not allowing repetitions, we're choosing 3 letters from all the possible letters. All the possible letters, there's 26 of them in the English alphabet, and we're choosing 3 of them to make up that part of the license plate. And so therefore we would have the number of permutations would be 26 times 25 times 24. That comes out to 15,600. Now for our total license plate, we have 3 letters followed by 3 numbers. Now we know that we're basically doing a product set with that, and so we would take our number of elements that we have for the letters and the number for the 3 numbers. And I just wrote down our choose 3 from 10 different numbers, 0 through 9. So the total number of elements that we would have, or the total number of license plates that we could make, would be 26 times 25 times 24, and then for the numbers it'd be 10 times 9 times 8. That comes out to about 11,232,000 different license plates. Now if we allowed repetitions, so in other words we could have a license plate AAA000, then we had a different number of possibilities. In this case, if we allowed repetitions, we would have 26 cubed for the number of possibilities for the letters, and then 10 cubed for the possibilities for the numbers. And the total number for that ends up being 17,576,000. So a big difference there if we allow repetitions. Let's look at another example. This one, how many ways can 5 people occupy 8 telephone booths? So we got 5 people. There's 8 telephone booths there, and 5 people are going to go into those telephone booths. So looking at this, we have to figure out, what are we starting with, and what are we choosing? Well, notice that you can kind of tell by the numbers that we're dealing with. We have 8 telephone booths, 5 people. So are we choosing people to go in each booth, or are we choosing booths for each of the people? Well, we're ending up with each person in a different booth. We want to know what booth those people are in. So what we're really doing is choosing a booth for each person. So we're basically choosing 5 different booths out of the 8 total that we have to choose from. And they're in order. We're going to look at this in terms of order. So we're not just choosing them, but we're choosing a booth for a particular person. And therefore order matters. So for the first one, we'll choose a booth for the first person. We have 8 ways of doing that. And when we choose a booth for the next person, we have 7 ways of doing that, and so on. So we're basically choosing 5 booths from the 8 that we have, and then putting them in order for each of the people that we're choosing for. Therefore, the permutations is 8 times 7 times 6 times 5 times 4 ends up being 6,720 different ways that those people can choose the telephone booths. Now in the next example, we've got 3 classes that we want to schedule, and we've got 5 time slots during the day that we can put them in. How many different schedules can there be? Well, we know that the class times are important, and if we arrange them in the same slots but different order, we know that that matters. So in this case, order matters. So therefore we're dealing with permutations, and we're picking 3 different time slots for each of those 3 classes from the 5 different time slots that are possible. So we've got a permutation of choosing 3 from 5, and that'll just be 5 times 4 times 3, and then that gives us 60.